Hello, my people. I hope we're doing well. This is one of those ones that's just going to be a whole lot of nasty notation. It's not altogether difficult. It's just one of those ones that I refer to as burdensome. But every once in a while, we just have to be burdened. We are calculus people, and that's just our lot in life, I suppose. This one reads, a right circular cone has volume V is equal to pi over 3 r squared h, and surface area is S is equal to pi r square root of r squared plus h squared. Okay, now that is, of course, the surface area of the outside of the cone. It doesn't include the base. Otherwise, it'd be plus, pi r squared. Find the dimensions of the cone with surface area of 1 and maximal volume. Now, surface area of 1. So I have two equations. This one is the one I'm maximizing, right? So I basically have V is equal to pi over 3 r squared h. But I have a problem, as I usually do, the fact that I have an equation of 3 variables and I really want to get it down to 2. So the question is, how am I going to use this over here to do that? And so I have 1 is equal to pi r times the square root of r squared plus h squared. Now, in order to solve for r or for h, I'm going to have to get rid of the radical, okay? And you might as well go ahead and square right here. Now, the difficulty in all of this is you might accidentally lose the square on that pi because you're not used to seeing pi squared, and you'll get going fast, and that square on the pi will all of a sudden disappear, okay? So be careful about that. So I have 1 over pi squared r squared, and then I have to, of course, subtract r squared, and that's equal to h squared. So h is equal to the square root of 1 over pi squared r squared minus r squared. And if you're thinking, gosh, that's ugly, yes, it is, okay? Now, the question is, of course, could you have done it differently? Like, could you have solved for r? And the difficulty comes in the fact that you have these two separate r's. It's going to be really hard to do it. You would actually have to figure out a way to treat r. Here, I'll indulge this just for a second. Once you get to here, you could go, well, that's 1 is equal to pi r to the 4th, or pi squared. See, I almost forgot the square on the pi. See, even I do it. So pi squared r squared h squared. Now, if we then turn it around and we have pi squared r to the 4th plus pi squared h squared r squared minus 1 is equal to 0, you would have to basically treat that like a quadratic, isolating r, but you would have to isolate r squared, and you would have to treat pi squared, but pi squared and h squared. Basically, this would be your a in your Pythagorean theorem, this would be your b, and this would be your c. So I guess you could do it. So let's see what we get. You get the opposite of b plus or minus the square root of b squared. So now you have pi to the 4th and h to the 4th minus 4a, and then c would turn that positive. Of course, again, I missed the squaring right there, right? All of that over 2a. Okay, well, that's not really turning out very well for us, okay? Because that's not a perfect square underneath there. It's messy no matter what. And this, of course, is going to take a greater feat of sort of ingenuity and strategy in order to arrive here. So here's the thing. I would suggest don't do it this way, okay? Just go ahead and do it this way. It's not fun, but it's doable. So we're going to use this and plug it in for h. But since this is a radical, and we are dealing with geometry, so we don't have to worry about those pesky negative numbers, and this is r squared is already squared. I don't have to worry about it possibly being negative. I can actually consider r squared as the square root of r to the fourth, so that I can combine it into one radical, and that might make the taking of the derivative a little bit easier. And so we have, and I forgot on the previous step to make it v of r, because at this point it is a function. And so we have pi over 3 times the square root of, and I'm going to put this as 1 over pi squared as a coefficient of r squared, just so that it's easier when I start taking the derivative. Now, v prime of r is pi over 3. That comes along for the ride. This is, of course, the radical is, of course, parentheses and an exponent of 1/2 times 1/2, and you get 1 over pi squared r squared minus r to the 6 to the negative 1/2. And then, of course, you have to take the derivative of the inside. And since this is the coefficient, I'm going to put a 2 over it and reduce that degree of r. And then, of course, do the same thing to the r to the 6th, although it doesn't have a coefficient that makes it, you know, icky. So this, again, like I said, burdensome, okay? Let's go ahead and simplify things just a little bit. I know that I can basically take this 2, take a 2 from in here, and get rid of that 1/2. That's going to make things a little bit easier. Not a ton, but a little bit easier. Pi over 3, and I'm going to have 1 over pi squared r minus 3r to the 5th. All of that over the square root, and I'm going to go ahead and do a little factoring within this radical down here. And I can go ahead and do a little bit of factoring up here in this numerator and take out an r. And I'm left with 1 over pi squared minus 3r to the 4th. Whew, yes, I know, it's exhausting. You get r squared and 1 over pi squared minus r to the 4th. Now, let's go ahead and let's take the numerator factor and set it equal to 0. So I have 1 minus pi squared is equal to 3r to the 4th. That means that I have 1 over pi squared is equal to r to the 4th. Now that's the numerator. Now the denominator, basically r squared and r squared, obviously the r here and the r squared here are going to give you critical values of r is equal to 0. That's obviously a minimum. And so you're going to have 1 over pi squared is equal to r to the 4th. Sorry, this has a 3 in the denominator. So you have r is equal to the 4th root of 1 over 3 pi squared, and r is equal to the 4th root of 1 over pi squared. Whew. All right, let's take a look at those values and see what they look like. So we have 1 divided by 3 pi squared, okay, and we're going to raise that to the 1/4 power, okay? And if we do that, we're going to get r is equal to 0.429. Now, when I, let's just go ahead and redo it, that's fine. So we'll do 1 over pi squared, and then let's go ahead and raise that to the 4th power, or the 1/4 power, sorry, and you get r is equal to 0.564. Now, we have to figure out which one of those is going to be our maximum. So let's go ahead, and I know it's kind of icky, but let's go ahead and put that function into here. So let's do pi over 3 times x squared times the square root, and let's go ahead and put that 1 over pi squared x squared minus r squared, or minus x squared. So now let's go ahead and quit that, and when we evaluate y1 at that value, we're going to get a volume of 0.117. If we evaluate y1 at this value, we're going to get basically 0, okay? So basically, this one is not going to be our maximum. This one is going to be our maximum. And we are actually asked to find the dimensions of the cone. So with that r, I simply, in order to find h, I simply have to, well, let's go ahead and just do it with this formula right here, okay? So let's do the square root of 1 over, actually, before we do that, let's take, let's take that, that value, and let's store it in for a. That's going to make things a whole lot easier, right? So let's do a fraction right here. We get 1 over pi squared, and then a squared minus a squared. I think that's right. Yeah. And that gives us an h value of 0.606. So h is approximately 0.606. Those are our dimensions which maximize the volume. Like I said, not fun, but doable, just burdensome, okay? Now this is one that I kind of skipped over because I kind of hit a roadblock and I didn't want to burn class time. But let's come back to it now that we have a little bit more time. And this is basically find the maximum area of a triangle formed by the axes and a tangent line to the graph. So, you know, if we have something like this, okay, we know basically that we have a triangle and it's going to be 1/2 base times height. And the base is formed by basically the distance from the origin to the x-intercept of the tangent line. And this height is going to be the distance from the origin to the y-intercept of that tangent line. But of course, the tangent line is determined by neither of those. The tangent line is determined by the point of tangency. Okay? So let's go ahead and label that, and let's call it, I don't know, let's call it t. T, and then of course its output is going to be 1 over t plus 1 squared, and that's our ordered pair. Now, let's go ahead and let's take, we know basically if that's the ordered pair, we need the derivative of the given function, and that's going to be, if y is equal to 1 over x plus 1 squared, or of course this is probably the better way to take it, y prime is negative 2x plus 1 to the negative 3, or negative 2x plus 1 cubed. Okay, well, I know that basically if I wanted to evaluate the slope of this function at that point, then y prime at the value t is going to be negative 2 over t plus 1 cubed. So now I have point and slope, which means I can use point slope. So y minus 1 over t plus 1 squared is equal to m t plus 1 cubed, and then x minus t. Okay. Now from here, basically from here we need to figure out the x-intercept and the y-intercept. So I'm going to go ahead and start another piece of paper because I don't want to basically run up against the bottom. So let's find our x-intercept, and of course our x-intercept is when y is equal to 0. And then let's find our y-intercept, and of course that's when x is equal to 0. So when y is equal to 0, we're going to have 0 minus 1 over t plus 1 squared is equal to negative 2 over t plus 1 cubed x minus t. When x is equal to 0, we're going to have y minus 1 over t plus 1 squared negative 2 over t plus 1 cubed times 0 minus t. So negative t. Okay. Let's figure out those. Okay. So let's go ahead and let's solve this one for basically our x. Okay. We need to know x in terms of t. So let's go ahead and basically we can multiply both sides by a negative, and then I need to get rid of this coefficient, so let's divide by it, and of course dividing by that is the same as multiplying by its reciprocal over 2. Well, that cancels out with 2 of those, and I'm left with x minus t. So I have 1/2 t plus 1, and then I'm going to add t to both sides, and that basically becomes 3/2 t plus 1/2. So x is equal to 3/2 t plus 1/2. There is my x value, and there is my basically my x-intercept in terms of t. So, I mean, x is not just equal to that at any moment. X is equal to that when y is equal to 0, right? So there's our ordered pair. Because basically I simply need to get the height of the triangle and the base of the triangle in terms of the same variable, and that's what's going on here. So let's go ahead and find y. So I have y is equal to, this becomes 2t over t plus 1 cubed, and then I need to add 1 over t plus 1 squared to the other side. Well, this of course needs to become t plus 1 cubed in the denominator in order to find a common denominator, and that's going to wind up being 3t plus 1 over t plus 1 cubed. So y is not just that value at any point. Y is that value when x is 0. And so I have t plus 1 cubed. Now I have the area in terms of both of those. So my area is 1/2 base, that's my x-intercept, right? Doesn't really matter which one you're multiplying by. So that's 3/2 t plus 1/2, and then this one is 3t plus 1 over t plus 1 cubed. Now if I pull out the 1/2 that is common to both of these terms, I'm going to get 1/4, and that's going to be 3t plus 1 squared over t plus 1 cubed. Now, and remember, this is a function. Like I said, this is another one of those ones that's just, it's not all that difficult, it's just burdensome. You have to do so many steps, and those so many steps, every single step opens up the possibility for a careless error, right? So just going to do product rule, chain rule inside the product rule to be more precise. So I have 1/4. Okay. Then I'm going to say, well, okay, well, let's do the first times the derivative of the second plus the derivative of the first times the second. Okay. Now, there's something common to both of these terms. Okay. There is in common a 3t plus 1, and there is in common a t plus 1 cubed in the denominator. Now, when I pull out both of those from the first term, I'm going to be left with 3t plus 1, because it only took out one of them, and t plus 1 in the denominator, and I'm going to be multiplying that by a negative 3. In this over here, I've pulled out everything, so it's just plus 6. But I'm going to need a common denominator, so let's, instead of just plus 6, let's multiply that by t plus 1 over t plus 1. And let's do another round of simplification. And this winds up being negative 9t minus 3 plus 6t plus 6. All of that over t plus 1. So you could actually, that becomes 1/4 times 3t plus 1. Now this winds up being negative 3 minus 3t. Okay, so 1 minus t, and this is t plus 1 to the 4th. Now all of that to get to a place where it's easier to actually find those critical values. But those critical values basically are, it's easy to discern which one it is, because this critical value is going to be negative 1/3. This critical value is going to be negative 1. This critical value, however, is positive. Yay! So basically, what this says is that the point of tangency is actually right here at 1. At 1/4, basically. Okay? Okay, so it asks you find the maximum area. It didn't ask me to find the t at which I have a maximum area. It asked me for maximum area. So let's go a of 1 is equal to 1/4. And let's go ahead and do it from this form right here. If I plug in 1 right here, I'm going to get 3 plus 1 or 4. 4 squared. 4 squared is, of course, 16. I'm going to plug in 1 right here. I'm going to get 2. 2 cubed is 8, and that's 1/4 times 2, or 1/2. That max area is 1/2. Now, burdensome, yes. Impossible, no. Okay? But you just have to be able to see how to transform it such that you can actually get everything in terms of that single variable. Now, remember, I teach way out in front, and then I sort of scale it back on the assessment. I won't give you one like this on the assessment, but I think it's really, really instructive for you to see stuff like this, see a little bit beyond where I'm going to actually write the assessments. And that's kind of why this problem is there. Notice that on the key to the worksheet, it was extra credit for whoever I wrote the worksheet for in the past. So, if you have any questions, as always, do shoot me an email. Bye.